Okay, there we go. Hello, everyone. Welcome to today's Corundum developer meeting. Today, I just have a few status updates. Just a couple words on the Zulu migration. Over the last week, I did some work on just basic interrupt rate limiting, just to see what that does to performance, see if that improves much of anything, and then basically the main other thing is the batch completion write support that I'm still working on. Still haven't gotten all of the kinks worked out of it yet, but I'm getting close. And then everything else is kind of carryover stuff from before, right? The VariableDescriptor Support, management software, and whatnot. So let's go over this stuff real quick. All right. So first up, Zulip. We've gone ahead and migrated from Slack to Zulip. I went ahead and ripped the band-aid off this because of the switch between 90 days or between 10,000 messages and 90 days for message visibility, basically on the free Slack plans. So for Zulip, they have their standard plan available for free for open source projects, which is pretty slick. And that has unlimited users and the full message history available. So whatever discussions we have on the public channels, that'll be visible in perpetuity. So people need to go back and reference stuff. It's all there. So I've gone ahead and migrated all of the public channel contents from Slack to Zulip. Unfortunately, I can't migrate anything from any of the private channels. So that history will be lost, but all the public stuff is there. And I also, as part of the process, all of the accounts were transferred over. So if you had an account on the Slack setup, all you need to do is reset the password on Zulip. And I have the chat or the link right here. It's the subdomain of zulipchat.com. All of the repositories and whatnot have been updated with this new link. If I've missed anything, please let me know and I'll fix it. I think I've got all references in the repository, in the wiki, and in the documentation, but it's entirely possible something has fallen through the cracks. So anyway, we're now on the new one. I'm still monitoring the Slack instance. If there's any discussion there, I'll direct it over to the Zulip channel and whatnot. But so far it seems like a fair number of people have gotten their accounts set up on Zulip. I also went ahead and created a channel for the MLE folks on Zulip, just like we had on the Slack channel. So yeah, that's squared away at this point. All right, so moving on to status updates for Corundum itself. So I guess it was either last week or the week before last, I decided to take a little step back from working on the updated queue or the descriptor write back code and just take a quick peek at the interrupt rate limiting to see if that does anything to the performance. Because when I implemented just the queue pointer write back support, we saw kind of a little bit of a degradation in performance. So the question is, okay, if we bring interrupt rate limiting to bear here and we limit how many interrupts we're generating, obviously this is not going to fix all the performance problems, because I think there's basically two things going on. One is that we're always writing the queue pointers back, and that consumes more PCIe traffic instead of just writing them in batches or writing them every few packets. So there's not much we can do about that with limiting the interrupts. But what we can do is interrupts after the first one will be delayed and you'll get a little bit of batching taking place. The first one doesn't really help very much, because you're still getting the first interrupt immediately after a packet is received or transmitted, instead of delaying that one for a few packets. But that kind of functionality, that's going to have to wait until we have the updated descriptor write code fully operational. But anyway, the interrupt rate limiting setup, it's pretty straightforward. The idea is that every time an interrupt is fired, there's basically a one-shot timer that gets started. There's one timer per interrupt channel. So if you have 64 MSIX channels, there's 64 of these timers. The first interrupt will fire immediately, and then it'll start the timer. on that IRQ channel, and then any subsequent interrupts will basically be recorded, but not sent until the timer expires. When the timer expires, then it fires off. If there was a pending interrupt, it fires the interrupt, and then it restarts the timer. If there wasn't a pending interrupt, then the timer, it turns off. So then the next interrupt on that channel will then fire immediately. Pretty straightforward. I think there's a number of devices that do something similar. So I implemented a simple IRQ rate limit module that does this, and there's a control register that specifies the interval in microseconds for all of the channels. Might make sense to rework that so we can specify on a per channel basis, but we'll start with specifying that across all of them. Internally, there's a prescale value to basically convert that value to microseconds, so it makes it nice and easy to use. So I've gone ahead and tested this with first pass. Oh, okay. So I have the register implemented, but I don't yet have any driver support for it to connect it up to ETH-tool or anything else. So, we'll flesh that out a little bit later. So I've gone ahead and tested this with kind of the first pass implementation of the Q pointer write back support, and it definitely helps with the performance. But I think in order to get the full benefit, we need the full improved descriptor write back code. So I went ahead and added one graph to the previous set that I had for the write back. So we'll go ahead and take a look at those real quick. So this is the baseline performance with 9K MTU. With write back turned on, we see a small variation in performance here. This kind of breakpoint away from full line rate on RX moves back a little bit from, where is this, about 10 queues or so, or I guess 10 iPerf processes. So you multiply this by 4 approximately to get the number of queues. So about 40 queues to about 24 queues, something like that. So this is with the write back support turned on, but we're still reading the Q pointers via MMIO. So we're issuing a bunch of additional PCIe writes, basically. Yeah, basically there's just that one small difference. So there is a performance impact, but it's not huge. With the improved support for writing the descriptors or writing the completions back out into host memory, hopefully we'll be able to batch some of these completion writes, and that may improve things here a little bit. We'll see once I get it working. Let's see. And then if I turn on the Q pointer write back support completely, so where we're actually using these written back pointers for in the driver for controlling what gets done next, then the performance drops a significant amount. And my suspicion is that this performance drop is coming from the fact that effectively the MMIO reads were sort of acting like interrupt coalescing, right? Because your MMIO read, it doesn't return immediately. It takes a little while, like a few microseconds, maybe, depending on conditions, for that read to come back. And that effectively delays when that first packet is processed after the interrupt, which allows potentially a couple of additional things to stack up in the queue. So if we're just reading this value directly out of DRAM, that happens immediately, and you lose some of that performance. So basically we're winning because MMIO is slow. So what we need to do is delay the first, the event and or the interrupt, such that a few packets can stack up in the queue before you process it. Unfortunately, we don't have a way of doing that with this particular variation of the code, but with the interrupt rate limiting, where not the first one gets delayed, but subsequent ones, that happens. Basically, this curve gets pushed up a little bit. So this is rate limiting the IRQs to 1 every 10 microseconds per channel. I haven't tried any other values. This is just a quick test to see if there's any performance at all. And actually, this is looking now quite similar to to using MMIO. So if we compare this and this, at least in terms of what this orange curve is doing, it's pretty similar. So definitely seeing an improvement here. It's not perfect, obviously, but it's a decent start. So that brings me to the batch completion rate support that I've been working on. The idea with this is that we have sort of a cache where completions can be and events can be aggregated across a small number of queues. And then once they're sitting in the cache, then they can be flushed out via DMA into host memory. And this effectively gives you interrupt coalescing because what we can do is delay the generation of the event until some timeout value. But unfortunately, this doesn't work in all cases because this is a cache. If stuff gets evicted out of the cache, either you have to have a way of keeping track of any remaining timeout value, or you have to generate the event immediately, in which case we're basically working like things were working previously when we didn't have this this write back cache. So the initial version of this is working in sim, closes timing and hardware, but it does have a few bugs that I'm still working on. Basically, at this point, I've narrowed it down to, well, I had some performance related issues that I think I've sorted out a little bit. It closes timing in hardware, but occasionally we're getting dropped completions causing stuck queues. So the way it works right now is well, just in general, the way Corundum works is every time you send a packet, there's a descriptor that gets generated describing, where the packet is located and whatnot. In response to that, the hardware will generate completion. So there's kind of a one-to-one correspondence between descriptors, packets, and completions. Right now, what's happening is that occasionally one of the completions doesn't get written out into host memory and the queue pointers and stuff don't get updated. Basically, it just disappears. And when the driver is going through processing the completions, there's basically a gap. There isn't a gap exactly because it just jumps to the next one. So you might have descriptor number 5, 6, 7, 8, 9, but then you have completion 5, 6, 8, 9, 10, shifted by 1. So I added some code to the driver to detect when that happens. So you get a message printout now. But now the trick is to figure out where in the code that's happening. I found a couple of corner cases that were related to that or potentially could cause that. I fixed a bunch of them, but it's still going on, so I haven't gotten to the bottom of it. I have ruled out a bunch of things. Like one thing I was thinking of, maybe there's a problem like on the FIFO where the completion is coming in from the component that generates the completion. But I've ruled that one out because there's a status response that goes back at the moment saying, yeah, that completion has been written and taken care of. That status response is being generated for every completion, because if it wasn't, then the transmit data path would hang completely, waiting for that. So because I'm not seeing the whole data path hang, it's just individual queues, ruled that possibility out. So still doing some work to try and narrow down exactly what's going on here. Code definitely needs some cleanup, but it's starting to show some signs of life. Basically, it'll run up to around 8 iPerf processes or so, at which point things start getting screwy. And basically what's happening is that if you run iPerf, it shows you the bandwidth for each of its connections, and basically each of those connections occasionally will get ones that drop to 0 when the queue gets stuck. And I think what's happening is for any connections over the number of queues supported by this little cache, once we exceed that number of queues, then one of the connections will get stuck. We'll lose a completion, the connection will get stuck, and then eventually we'll just be running with the number of connections that fit in the cache. And then nothing else gets dropped. So yeah, I haven't gotten to the bottom of that yet. Hopefully I'll be able to get that sorted out soon, but we'll see. Let's see. There's one other thing I was going to mention as well. Oh, yeah. I did notice one other thing in terms of performance. That's not necessarily all that great. This is kind of a higher level thing that we might have to think about if there's any potential solutions for this. But basically, one thing I noticed is that when I had an earlier version of this that worked all the way out to 16 iPerf processes, but didn't have very good performance, basically the performance ramped up until it hit like 6 queues, and then it dropped precipitously. And what I realized is that once it fills up, 6 queues, so the way I had it set up is with 24, the queue management logic had 24 of these slots that could be used on the hardware. So once we got up to using 24 transmit queues, then I had to start, kicking stuff out of the cache basically in order to send more data. And because Corundum has a round robin transmit scheduler, if you have 64 queues lined up to send, you basically get no benefit from the batching, because it sends one from Q1, one from Q2, so on and so forth. The first 24 will fill up the 24 slots. The next 24 are 24 cache misses. Basically, it'll kick out all 24 slots. So basically, in the worst case, I had to kind of rework things such that it'll fall back on the previous behavior, where as soon as the completion shows up, it'll immediately trigger the DMA write out into host memory, so it can free up that slot again for a totally different queue. So once I've made those changes, I'm no longer seeing that performance drop, because we start getting stuck queues. So yeah, there's still some corner case or some race condition that's causing things to get screwed up that I'm working on. But yeah, so at some point I'm going to have to revisit the transmit scheduler in Corundum, and if we do something other than pure round robin, I think we'll get more benefit from the queue management here, because that's going to allow these caches to work a little bit more efficiently. Anyway, that's about all I have to say on this, because it's still a work in progress. And everything after this is basically carryovers from last time. Right, I have a couple more details on the completion write support. That's same as what I showed last time. And then once the completion write support has been squared away, then I'm going to take that code and adapt it so it'll work for variable length descriptors. So it's well, I mean, obviously it's not the same code, but the variable length descriptor support needs kind of a similar caching setup, where we'll dynamically assign, sections of an internal memory for the descriptor rings just in the RX direction. So yeah, once I get the kinks worked out of that, then variable length descriptor support is next up on the to-do list. So that could take some time to get stuff squared away. Oh, one thing that I did do is I went ahead and I dropped the ARM continuous bit in the queues. So I mentioned queue state storage before. I have a new module for that. So the queue state storage here, previously it looks like this, and the new one, it looks like this. I added the LSO offset and the VF index, and changed a bunch of the pointer sizes to free up a few bits. So I guess mainly I changed the base address size. But I also got rid of the ARM continuous bit, because that adds a lot of complexity in terms of managing when to generate events and whatnot. Previously, it was pretty straightforward. The ARM continuous bit, if you set it, it just prevents the hardware from clearing the ARM bit. But I don't know if anybody's actually using that bit. I went ahead and implemented it because it's like, okay, that's an easy thing to do. That might be useful at some point. But with the current setup and the more comprehensive descriptor write back handling code, it was unclear exactly how to handle that capability. Because with timeouts and limits that'll trigger event generation and things like that, then becomes a question of, I don't want to be generating these events continuously. Like if you have more than the packet count limit in the queue, I don't want to be firing off like a million events per second or something like that. That would be stupid with the ARM continuous. So you would need to have some additional state to prevent that from happening. It adds a lot of additional complexity. So I'm like, okay, I'm just going to drop that bit for now. If that is functionality that somebody needs, we can think about adding it back later. But I don't think it's necessary really, because when you're processing stuff, you're going to want to go set that to go back into polling mode. Without that set, you can still read the queue pointers out of host memory if you want, and everything works just fine. So not a big deal. I think that's about it in terms of updates. I still have the carryover to do items, softcore, 10G25D switching, and the clock register block that I need to implement. Oh, I guess one thing I should mention is that as part of adding the interrupt rate limiting, I also added a couple of parameters to basically inform the HDL design of the logic clock period, so it can compute prescale values for the interrupt coalescing components. And then I'm also going to use that for the descriptor write-back support and the timeout values that are used by that code. So the clock info register block can also be used to expose that information to the driver as well. So some point, once I get some of this stuff squared away, I'll go ahead and sit down and get this thing implemented. Right. So that brings me back to the to-do list for the stable release. Variable descriptor support is now in progress. So as soon as I get that done and everything looking good, then we could probably start cutting versioned releases, which will be useful. All right, that's about it in terms of updates. I'm not sure if anybody has any questions, comments, or discussion points. So I'll open it up to everybody. Thanks for listening in.
Hey, Alex,
So,
this is
Bob?
a quick question.
Sure.
So you talked about interrupt coalescing. Well, I don't think you're going to do it with eTool because of all the queues, right? So are you going to have an interface from the host to set some of these parameters, or what's the plan?
Right. Well, so ethtool has some settings that are going to be used to set the not the interrupt coalescing directly, but the basically write back timeout and packet count settings. Because I think ethtool, it gives you for both RX and TX, you can set a number of packets and a timeout value. And I think a few other things too. It's got like some rate-based settings and it's got a bunch of stuff.
It's got a high
Not
low.
every driver implements all of that.
Yeah.
I was looking at a couple of drivers just to see kind of what was done. I think the I think I was looking at one of the Intel NIC drivers. I don't know if it was IXGBE, and that one implements like, what does it do? I think it's only
it has a
packet count, something like that. Yeah, it's not much. I think it's only the receive side too, maybe. I can't remember, but yeah, it doesn't implement a whole swath of different settings. So the idea is that I'm going to point the ethtool settings at the at kind of the per TX and per RX settings in the updated descriptor write-back logic, which is separate from the interrupt rate limiting logic. So the reason I went ahead and implemented the interrupt rate limiting thing is that when you're using a whole bunch of queues, it's not going to be respecting the timeouts. It's going to be generating the events earlier than you would want potentially. So because of that, it makes sense to have that interrupt rate limiting in that particular case. But I'm not sure the best way to expose that, because I don't think ethtool has additional options that affect both TX and RX. So I'm not sure about that. One thing I was looking at is, what the Mellanox NICs do, because they have there's a manual that describes everything that that describes kind of at a high level what the interface is to talk to the NIC. So I was looking at that and then matching that up against what the driver was doing to try and figure out how the ETH tool interrupt coalescing parameters are implemented. And it seems like they're not even touching their interrupt rate limiting capability. They're only adjusting the per queue settings. And with ETH tool, they basically are handling those APIs. They basically loop over all the queues and set the value the same on all the queues, which, you know, that makes sense because the ETH tool APIs don't specify you know, which queues you're trying to adjust. It's just those values on that particular interface. So I don't know if you can do much better than that, unfortunately. And I'm not sure how they set the, you know, kind of the default setting for the interrupt coalescing. It could be just turned off, so they're just going straight through. Not sure. That's probably going to require a little bit more research. I don't know if anybody else has looked at any of the other network drivers to see if they're doing anything particularly noteworthy in terms of the interrupt coalescing.
Well, for latency, we turn it all off. So
well, yeah, obviously.
Yeah. So,
you guys would not be doing that.
Yeah.
Well, I mean, do you even use interrupts, or do you just poll? Right?
Yeah, it's mostly polling. It's polling, fixed poll. Yeah.
Because the interrupts, you know, there's quite a bit of latency involved with going through the interrupt controllers and yada yada yada. So.
I mean, the other cards I've worked on with ASICs, yeah, they had some settings, and normally they came with, I think, some coalescing on. And we, you know, when we were doing latency testing, we just turn it all off. And,
right, yeah. Yeah, so the way I have the interrupts set up, well, so I guess there's two different kind of aspects to this. So the coalescing is implemented when the events are generated and the interrupts are generated from the event queues. So with that, it can hold off the generation until it sees a certain number of events or a certain number of packets, or there's a certain timeout value associated with that. The interrupt rate limiting is slightly different because this isn't looking at any additional state. So the first interrupt that comes into the rate limiter goes through immediately. It doesn't get delayed at all. It's just subsequent interrupts get delayed. So if you have, you know, a high amount of traffic on one interface, well, if you have a high amount of traffic, then it should presumably just run in poll mode without re-enabling interrupts. But if you are generating interrupts back to back for whatever reason, then it'll be rate limited to, you know, whatever the period is on each of the separate channels. So I'm actually not sure how big of an impact this would have on the latency, because the first packet that gets, you know, the first interrupt that gets fired off doesn't get delayed at all. And then for some time, you would think that, you know, NAPI will be doing its polling, in which case you're not using interrupts, it's just reading the queue pointers and whatnot. So probably going to require some experimentation once some of the pieces are working. But yeah, that's definitely something I've been trying to figure out. Is like, if we want to play with this, how do we expose it? ETH tool we can use to expose some of the parameters, but they don't have, they have a slightly different set of knobs. I'm not going to say they don't have enough knobs. They have a slightly different set of knobs.
They do. Okay, that's all I had. Thank you.
All right. Anybody else have any questions or comments?
Well, not really. We just are looking forward to have interrupt coalescing one day in QNIC, obviously.
Right. Well, so the
due to performance
stuff, yeah. So the interrupt rate limiting stuff, you should be able to pull that from, you know, my development branch right now and take a look at it. You could probably backport that as well. That's pretty simple code, and the modifications required for that are pretty straightforward. It doesn't really affect the resource consumption very much. Right? It's just one module that sits in front of the MSIX block, basically. So
Okay.
You might want to take a look at that if you think that's
Yeah,
gonna have a
might be
significant
interesting.
impact
Yeah.
on performance, because that's going to be a much smaller change, much lower, much more reasonable than the improved descriptor or the completion write back code, which I'm working on. That's a much more extensive change. That's that could have a much larger impact on resource consumption and whatnot.
Yeah.
But yeah, I've definitely had some people ask about that, so figure okay, let's take a look and also see what it does from a performance perspective. And
Yeah, I guess for the for kind of the middle ground where there's no strong requirement in terms of latency, for example, like Bob mentioned, this makes sense since it just lowers the CPU load significantly.
Right, yeah.
We are currently looking at what a modern Intel card does and what MQNIC does, and it's I think it's not overstated if I say it's day and night in terms of CPU load.
Well, I guess there are a few other things that most other NICs do that eventually I want to get Corundum to do in terms of TSO, which reduces not just the number of interrupts, but the number of basically packets that are handled by the network stack. So yeah, at some point, hopefully we'll be able to get at least TSO working in Corundum. As far as on the receive side, that's a slightly different ball of wax. So I'm not sure if we'll be able to do any kind of receive coalescing in the near future, maybe. But the two of those will also help improve performance. Yeah, and I know Intel and Mellanox are implementing that sort of thing. So between that and interrupt coalescing, yeah, that should definitely help with the performance quite a bit, especially on lower power devices, I would think.
Yeah, it turns out currently, at least in our case, that it does not affect the maximum bandwidth, for example, but the CPU load is just
right. I guess it depends
high.
on where the throughput is, or where the bottleneck is, right? Because if you're limited on the CPU, or if the CPU is limiting the throughput, then yeah, you're obviously going to be limited there.
Yeah, I mean, obviously for our second device, we're working at based on Sync on the ARM chip.
Right.
There, the need for it will be even bigger, I would think, since it's way less powerful than an Intel server.
I guess, yeah. So I think it's going to depend on where the CPU cycles are being consumed. But I mean, obviously, the less that are consumed by the network stack, the better, because whatever the network stack is consuming, you can't use for applications or whatever. So yeah. If you're just running iPerf and you just have a 10G link, you're not going to be CPU limited. Because you're going to be running at the line rate of the link. You'll be limited by the link rate. But yeah, if you're running it on a 100 gig link, you'll probably end up being CPU limited instead of limited by the link. So
yeah.
Anyway, yeah, I guess that's another thing too, is with like previously over PCI Express, you do get some sort of interrupt coalescing benefit from the MMIO reads because they take a while. But on ARM, presumably those MMIO reads would be quite fast because they're just going over AXI internal to the chip. So you're not going to be getting as much benefit from the from that delay, because you have less delay. So I have not tried running with the interrupt rate limiting on one of the Zynq devices. I should probably try that to see if it makes any difference.
Yeah. Interesting. Yeah, would be interesting.
All right. Well, I don't really have anything else to mention for today. Does anyone else have any questions or comments? Going once, going twice. All right. Well, I guess we'll adjourn for today and pick it up in 2 weeks. So thanks to everyone for tuning into the meeting today.
All right. Thanks, Alex.
All right. Talk to you.
Bye.
Thanks. Bye.